No. All right, so what did we do yesterday? Well, there's a Cauchy-Schwarz inequality, and we start talking about linear operator. We see some familiar operations like the adjoint, which can be used to characterize Hermitian operators, our old friends, and unitary operators. And in Quantum 101, textbooks would usually focus on Hermitian operators, especially the fact that its eigenvectors form a complete orthonormal set, or rather that it's complete and then you can choose it to be orthonormal. And there'll be some lemma, like if the when you have different eigenvalues, then the eigenvectors or eigenspace that correspond to those eigenvalues would need to be orthogonal, for example. But yeah, for this class, for quantum information, we would generalize that a bit to statement about normal operator instead, which is an extension, is kind of like a bigger class that include Hermitian operators. And well, but still there be reasons that we can focus on Hermitian and unitary operator, for example. Okay, maybe this is a good point to emphasize that as you know, unitary operators are also diagonalizable in the sense that their eigenvectors also form a complete set and span the whole space, and they can choose them to be orthonormal. But why are we focusing on Hermitian operators in Quantum 101? It's so what are the difference between Hermitian and unitary operators in the, like, say for so their eigenvalues? Eigenvalues Hermitian is, I don't know how many percent. It can be real, right? Like the eigenvalue of position operator, you have both plus x and minus x. Yeah, if it's positive, then it's a subclass called positive operators. Yeah. Meanwhile, so it's a good some visualization is that if I have a complex plane, right? So an eigenvalues or the so-called spectrum. Mathematicians usually use the word spectrum to call the set of eigenvalues. For Hermitian operators, can be anything on the real line. But for unitary operator, is anything, any complex number that has modulus 1. Yeah, so it can be plus 1, minus 1, but it also can have arbitrary phase. And so, of course, if you have operators that are both Hermitian and unitary, like the Pauli, the qubit Pauli, then of course, right, then it means that your eigenvalues are necessarily 1 or minus 1 if it's both unitary and Hermitian. Okay. And yeah, as you gave an example, if it's positive operator, this is the spectrum of positive operators, which we haven't really talked about yet. But they will become important later when we talk about density operators, which represent the state in quantum mechanics. Okay, so last time we have left off talking about characterization of unitary operators. Let's see, so maybe I should write something like this to remind you about other topics that we talk about as well. So Hermitian operator is a Dagger when is equal its own Dagger, and eigenvector can be chosen to form an ONB. So suppose I call the eigenvectors A sub j, then in Dirac notation, the operator A can be written like this. So this is just a recap, and we also talk about if there is a degeneracy in these eigenvalues, then you can further group them into a sum of projectors onto eigenspace, right? So sort of if you imagine a vector space, kind of like some blob going on, then if all the eigenvalues are different, then this means that if you partition this into subspace of the one-dimensional subspace spanned by each eigenvector, so it's like A1, A2, right? So when you act on each subspace, because it's eigenvectors, you would get the eigenvalues back, and then the vector remain the same. But if it's degenerate, so for example, if A1 equals A2, right? Then you have a subspace that is more than one dimensional that are invariant under A, and then when you let A act on this subspace, then any vector, any linear combination of vector in this subspace will get the eigenvalue A1, for example. In particular, if I have a degeneracy label here, right, then what we are saying is that I can further group them into this. So if A if AJ alpha equals AJ beta, so meaning that if it's the same J, then it has all the same eigenvalues, then I can write this, where the Pj is a sum of one-dimensional projector onto the subspace with the same eigenvalues, right? And that subspace is usually called eigenspace. Can you say that again? Subspace of an orthonormal basis is a set of vectors, right? Eigenspace is a set of vector space. Yeah, so you can partition. So given a Hermitian operator or later on normal operator, you can partition the vector space into a direct sum of orthogonal eigenspace. Yeah. But if you want to talk about a basis, then the basis for the eigenspace or a subspace in general can be chosen from a subset of a basis of the whole space, right? Okay. And then for unitary operator, we list some characterization. So the definition. So this is the definition. Right? And then last time we also gave a short proof of why in finite dimension, if this equality is true, then the order is also true. Right. Yeah. Right. And then I gave a few ways to characterize the unitary operators that are all equivalent. This one is preserve. Any question? Yeah. So if you don't have this, right? Yeah. Yeah. We can. Yes, everything that it can be diagonalized is a subset of normal operators. So from this definition, implies that unitary operators always preserve the inner product. Yeah. And you can see it, right? Because if I have an inner product, if I transform the cat by u, then I have to transform the bra by u dagger. And so if you take the inner product of whether you take the inner product of the bra and the cat, or the bra and the cat after you apply u, then it's the same, because the u dagger and u combine into the identity. Another way to say the same thing is that you send an orthonormal basis to an orthonormal basis. Right. Different orthonormal basis. Since it preserves the inner product, right? So it preserves the orthogonality and normalization of the vector. Which is this can be expressed quite conveniently in Dirac notation, because you can say that if I have, let's say, an O orthonormal basis EJ, and the new one, the E prime J, just to easy to remember, the prime is new in this example. Then how would you write this unitary that maps between from the old basis to the new basis in Dirac notation?
Just for normal basis. Check orthonormal basis and graph of new.
So bra of new, right? Yeah, exactly, right. Because whenever you input the vector EJ, then you get the new basis vector EJ prime. Yeah. So of course here and here we can see the advantage of the Dirac notation, right? That you can express linear operators in yeah, you can express the linear operator from the way it acts. Right. The right side is the bra is the input, the ket is the output. For example, now if say you're in linear algebra 101 class, someone will ask you to write down the change of basis matrix. So now if you change from orthonormal to orthonormal basis, the change of basis matrix has to be unitary. And now you can write this easily, right? So usually people would write in the O basis, right? Because we start in the O basis and we try to map vector in the O basis to the new basis. So what would the matrix element be? Yeah. So if I try to write in the O basis, right? So I would just compute this sandwich. And now I already used J and K. J here is a dummy operator, dummy index, so I can change. So EJ, L prime, EL, and then EK. And so this becomes, and so what you're left is, so the sum disappear. And then here, I just have that is the row in the old basis and then the column in the new basis. Right. And so on. Unitary. And then the last one that we talk about is the columns or rows of U. So columns of U are the rows of U dagger, right? Form and O and B. This is the same. Can you see why this is true? So for example, the columns. Can you see why this property is true? For columns, for example, why do columns of U have to be orthonormal?
Because if it dagger, if it represents and then by using the definition.
Right. So the definition is just really just express the orthonormality, right? Yeah. And another way to say it is that when I input the first for when I put the jth elements of the O basis, so like EJ, then I get the EJ prime. And this EJ prime is the column, is the J column of the U. So they have to be orthogonal. Yeah. And well, before we move on to normal operator, maybe I want to say something like this real quick, that if you have functions of linear operator that are diagonalizable, that is when I have a function of a that is now is either Hermitian or unitary. The easiest way to apply this, so in general, for example, if the function is analytic, so for general operators, if they're not diagonalizable, then you would have to what would you do? For example, if the function is analytic, that is, it has a Taylor series, and you have to expand this f of a into a Taylor series with matrix argument, right? And this is something that, I'm sure everyone has done at least for once in their life. For example, the exponential function. But if a is diagonalizable, then you would just do the spectral decomposition. There's many names like eigen decomposition, spectral decomposition, diagonalization. To get this, and then you get the eigenvalues, and then now you apply the function to the eigenvalues. For example, in quantum mechanics, when you have unitaries, you write it as, well, I guess there are either way. Unitary is, every unitary is generated by some Hamiltonian, and conversely, if you have a Hamiltonian which are Hermitian, then you can exponentiate it to get a time evolution unitary operator. But this is also like a general statement in linear algebra that you can make in linear algebra as well, minus the h bar. I mean, I just mean that h bar doesn't have any meaning in linear algebra, right? But it's still always true that if you exponentiate an anti-Hermitian operator here, just because that's I, yes, then you will get a unitary operator. So here mean that I can write u as I can diagonalize u in the eigenbasis of the Hamiltonian, right? Which I would call this, which are the energy eigenstate, En, E sub n. And then if this is the Hamiltonian, the eigenvalues here would be the energy E sub n, right? But now for this unitary, the eigenvalue would be just apply the function to the eigenvalue directly. All right. Yeah. So now those are stuff that you might have seen before. Now, yes, as Cham say, or to paraphrase, we'll get to the matter of all diagonalizable operators. So this is, the definition is that we call an operator normal when A commutes with its own dagger. So in other words, right, so these two are the same. And you can already see that Hermitian operator is a special case of this. Unitary operator is also a special case of this. Projection operator, but projection operator is already Hermitian, so yeah. Yeah, so basically most of the things that we care about in quantum mechanics are normal operator, except where they don't, when they are not normal. And for example, I believe in homework 2, but I'm trying to remember the number of the numbering of the problem. I mean, there are two problems. One is for normal operator, and the one is for non-normal operator. Yeah, let me just open up. Okay. 2, 3. Normal operators for qubits. And then non-normal operator. And a prevalent example would of a non-normal operator would be, for example, the creation operator. Oh, sorry. Yeah, this is the annihilation. If I label it like this, right? So, yeah. Okay. Let's see. Yeah. So what we can say about normal operators? Well, it turns out that it's the biggest class of operators that are diagonalizable. So, meaning that it has a complete orthonormal set if and only if it is normal. No, it's the word it. Sorry. Have any of you seen the proof that normal operator is diagonalizable?
Exponential.
I don't see how. Well, it depends on what you allow as your original assumption, right? So for example, if you already assume that permission operators are diagonalizable, then it's not so hard to show that normal operators are diagonalizable as well. Why, for example, so maybe a remark. Then it's just not so difficult to show that the same thing happens for normal operators. And there are probably a few ways to do this. But for example, I can write, for any linear operator, I can write it as the real and imaginary parts. So let's say I write it like this, where both F and G are Hermitian. So why is this true? Yeah. Yeah. Do you know how would you write H, for example? Of A, yeah. What would it do? And this would just be minus, right? But wait, but if you don't have like H and G, yeah. So you this can be done because you can do things like this, right? So if you have A plus A dagger, then this is Hermitian, right? Whereas if you do it the other way, if you have A minus A dagger, you would have something that is an anti-Hermitian, which so anti-Hermitian is no, because I say that G is Hermitian. That's why I put the I here, so that this whole thing is anti-Hermitian, and so this is Hermitian. Right, so G, so if I only have this, it will be anti-Hermitian. But then, yes, depend on how you choose this, right? Maybe I put it here, usually. Yeah, yeah. Yeah, so you can basically, for any operator, any linear operators, you just sort of basically add and subtract a dagger, and this is how you get the real and imaginary parts. And then you can show that, and I'm not gonna do this, but the fact that the real and imaginary part commute implies, and also conversely imply, that A and A dagger commute. So it's just a few lines of algebra. But once you have this, you're good to go, right? Because now, if you assume that Hermitian operators have a complete or non-normal set, and maybe further, you also know that if two Hermitian operators commute, then you can choose a complete orthonormal set that are eigenvectors of both operators, right? And so here in this case, so now if you say that A is normal, it means that this is true. And then because of this if and only if condition, it means that the real and imaginary part also commute. And therefore, you can, if since both of them are Hermitian, you can diagonalize both of them. But in particular, in this case, because they commute, both H and G are diagonalized in the same basis. And so that's why A, the normal operator in A, is then diagonalizable. If you don't assume that Hermitian operators are diagonalizable, because usually Quantum 101 books doesn't show you either why, there's another way to directly prove that this is diagonalizable. So we're not gonna do that, but the sketch of the idea is, for example, you can argue that if linear operator is diagonalizable, it means that if a subspace, let's see, how do I say this? Okay. So let W be an eigenspace, or should I say A eigenspace? So let's say A is diagonalizable. Yeah, let's say W in the Hilbert space. Yeah. So in other words, it's an eigenspace of A. Okay, I think to make this statement more uniform, yeah, sorry. Let's say this. Be a subspace invariant under A. And A here, invariant under A here means that whenever I apply A to that subspace, what I get out is still in the subspace. So for example, if I have a vector in W, then the statement is invariant, means that A acting on psi would still be in W. So the statement here is that this is equivalent to if W is an invariant subspace. I don't know why I write it again, but then the orthogonal complement of W. So it's just subspaces that all the vectors are orthogonal to vectors in W. Is also A invariant. Well, maybe I should be careful and say this is in vector space over complex number C. Well, why is this the case? So the rough idea is that in the complex field, it turns out that every linear operator must have at least one eigenvector, like at least one eigenvalue and one eigenvector. And that's just because when you solve for the eigenvalue, right, from the first principle, you would find the solution of the characteristic equation. It's like the determinant of A minus lambda I. So in a real vector space, so if the coefficient of, if you only allow real solutions, then it's not guaranteed, right, that the polynomial equation has a solution. For example, right, because the solution here is just I, which is not real. And the complex number is introduced precisely to make any equation solvable. And so is what is called the fundamental theorem of algebra, is that every polynomial equation in complex number had at least one solution, or it can be factored. Actually, it can be factored completely into like product of like z minus the solution. And that's ultimately the reason that every linear operator in complex vector space has at least one eigenvector. But now, if this property is also true, so if you have one eigenvector, then that means you have at least one dimension of subspace that is invariant under A. So it's okay. Eigenspace are also invariant subspace, right? Because invariant doesn't mean that it doesn't do anything. It just it does not mean that it doesn't do anything. It can multiply by eigenvalue, right? Because when you act, when you let a linear operator act on its eigenvector, you get an eigenvalue, right? So it actually does something. But so it's not like an identity operator. It still does something to the vector in that subspace, but that still fits in the definition of invariant. So here it just means that if I have a vector here and then I act, then it's still in the subspace. So here in this case, if psi is an eigenvector of A, and then I let A act, then I will get the eigenvalue, right? which is of course is still in this subspace, right? Because you just multiply it by scalar, right? Yeah, and so having an eigenvector means that you have an A invariant subspace. But then if furthermore this statement is true, it means that now you can consider the action of operator A on the orthogonal complement here. So it's, you reduce it to be a smaller vector space, like minus one dimension. And now you can consider A to be an operator in there, right? And now again, since you're in the complex number, you can find one more eigenvector. And then you keep repeating this until you get all the eigenvectors that are complete orthonormal set. So that was the explanation of why these two statements are the same. And if you have any question, please ask, because it's yeah, it's quite a mouthful to say. Yeah, but the upshot is these two are the same, and so to show that, one way to directly show that a normal operator is diagonalizable is to show that this is true. And I think this is the way that Nielsen and Chuang. So I'm not exactly, I don't exactly remember, but apologize, this is wrong. I think it's like box 2.2. And I think I have seen the proof of this. I mean, not the proof that of the equivalence of this, but the proof that if you have a normal operator and this is true. It's somewhere on Wikipedia. I don't remember where. Maybe it's a page on normal operator, if I have to guess. Yeah. Yeah. Right. Good. So now that if you believe that normal operators are the biggest class, well, I guess I'm not sure what I was gonna say after that. After putting it that way, then we can visualize other operators we have known so far as a subclasses of normal operator. For normal, this is like a big set. Then of course I have the Hermitian operator as a subset, right? Then there's also positive. So there's a positive operator. And then there's a projection operator. So here I did not actually give the definition of the positive operator, but if you assume, which is true in this case, that they have to be Hermitian, then they're just Hermitian operator whose eigenvalues are all positive. We're gonna get to that, but at least this makes sense, right? That you have this hierarchy, because for Hermitian operator, eigenvalues can be anywhere on the real line. For positive operator, it has to be on the R plus, the positive real line. And then for projection operators, the eigenvalues can only be 0 or 1. Right? And now I'm going to draw the box for unitary operators, right? But of course, it cannot overlap with this box because projection operator has eigenvalue 0. Yeah, projection has eigenvalues 0 and 1, right? Yeah. Or 0 or 1. But unitary operator cannot have 0 eigenvalue. And so it cannot overlap with this box, but it can overlap with this guy. Let's say this is unitary, right? So, right. So what would be an example of something in here that are both Hermitian and unitary? Okay. And then also this guy. What can their eigenvalues be?
Must be a bit of shape.
Yeah. So what would that set look like? Yeah, I mean, intersection of real and the eigenvalue of unitary, right? So what are the possible eigenvalues for unitary operators? Not really. What are the set of eigenvalues for unitary operators?
Any
No, right? We draw earlier that it has to has unit length, right? So not just any complex number. No, any complex number with unit length. Like we draw this earlier, right? That yeah, yeah. Right. Uh, well, the real light is here, right? So what is yeah? So do you know an examples of such operators? Yeah. 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 Yep. And beyond this big square, nothing is diagonalizable. It's diagonalizable if and only if the operators are normal. Mhm. Mhm. Yeah, and so to emphasize the thing that we already talked about it again, now we have now we know, right, that if Now we can take any function of normal operators by applying the function to its eigenvalues. It's the same way we did with the Hermitian or unitary operators. For example, you already see this, that okay, we'll just forget the physics. There's no time, no h bar anymore. If this G is Hermitian, then U is unitary. We already see it. We already saw it. But for example, you can do something like this as well. So let's keep the G. By this is the where this is just a shorthand for sorry. For no eigenvalue of G is 1, just to make this non-zero, not blow up, right? Actually, this is another map that another function that map Hermitian operator to unitary operators. Do you see why? Do you see that it's actually unitary? Yeah. So let's work it out, right? That if I multiply this with the dagger, right? Oh, sorry. Well, I mean, you can write it like this as well, but let's be more careful because as I wrote here, this is just a shorthand, right? Usually, you should not write like you should not divide a matrix by another matrix. But this works because everything is diagonal in the same basis, right? Identity is always diagonals in any basis. And so if you write, you can write this expression in the eigenbasis of G, and then replace G by its eigenvalue. So if I take this and then multiply by its dagger, right? So then this would be the guy, the same guy, and then well, it's okay. It's switch the order. Let's see. Actually, does this work? Oh, not quite, I think, the way that I think about it. Yeah, maybe I will try to think a bit about it again. Sorry, but this is called, do I even have a name? Oh, Cayley transform. Cayley transform. It turns out to be another way to map Hermitian operator to unitary operators without using the exponential, or equivalently without using the infinite series that come with the exponential. And for example, I use this in the fermion sampling paper to prove the quantum supremacy. Right. So I think for the last 30 minutes here, I want to talk about, well, what you can do when you don't have normal operators. Well, I guess you can do many things, but at least there are two things that I want to talk about. One that I guess everyone should know. One is the polar decomposition, and the other is singular value decomposition. Oh, sorry. So for example, okay, which one is called left and which one is called right? Dropbox up. Left is PU. Yeah. Let's do the right one. So for any linear operator, you can write it as a product of a unitary operator and a positive operator. And can you guess why it's called polar? This is positive. Yeah.
We can write elements of unitary in a program.
Maybe. I think the reason is that, so here we start to see, so this is sort of the way that, one way that we can sort of look at operator as kind of like complex numbers, right? Because here I decompose an arbitrary operator into its real and complex part. But here, what are the eigenvalues of the unitary is just some phase, right? And then for positive operator, it's just some absolute value, right? And of course, this is the polar decomposition, the polar form for the complex number. Well, maybe it's not Z. Sometimes it'll go right as R. Yeah. Yeah, and so you can do this as well to not just a complex number, but also linear operators. Except that now U and P don't have to commute, unlike here, where everything commutes, right? Well, why is this true? So the sketch of the proof. So, okay, maybe first let's just look at the formula and think about what it means, right? So it means that, oh, and by the way, there's another version called the left, which you just put the positive operator on the left. So here it just means that applying some linear operator, like some arbitrary linear operator, right, is the same as stretching the vector. So here for positive operator, you can diagonalize it, right? And then the effect of P on its eigenvectors would just be to scale the eigenvectors by a positive number, right? So which means stretch or squeeze the operator. Actually, it can flip the eigenvector as well. So you could in general you could like say that this is Hermitian operators and not just positive. But on the other hand, you can always choose it to be positive because you can put the sign in the unitary operator instead. Put the minus sign in there. So P is like stretching or squeezing, and then U just rotate. Right? So U is a unitary, so it preserves the norm. So it just changed the basis from orthonormal basis to another orthonormal basis. So this is a statement. So for the left, polar decomposition is the opposite. It just means that when you apply A, you first rotate and then you stretch. So the idea of why this is true is usually is first to show that for any vector, okay, do you have any idea of what this P should be? No, the positive part. A? Yeah. So it must relate somehow to A, right? Do you have a guess, the cameraman?
Just see somewhere.
Can you guess what would it be the expressions of this P? Yes, when you do the polar, then you have to calculate the U, and so given A, you have to calculate U and P somehow, right? No. But if it's identity, then I don't need it, right? Yeah, something like that, right? So so for any operator A, both of these are always positive. And can you see why? Is it clear? So I think for this is maybe is the most clear if I start with the general definition of the positive operator, which is that yeah, if A is positive. So the way, let's see the time. Yeah, there's still time. So the way to see this, right? So for this one, so if I put it here, then I can consider this and this separately, right? And this would just be the bra that's corresponding to this kit, right? And so therefore, this is just the norm square, which has to be positive. It's the same for AA dagger. So then in particular, if they are positive, it means that it has a unique positive square root. Okay. So can take square root. Or the other way around as well. So now, for example, if I take let's see, if I take P, let's make a guess. If P is A dagger A, and then, yeah, if say P is the square root of A dagger A, then what if I multiply this? So suppose that this is true, right? So A dagger A, so then it would be U, A dagger A, and then the dagger of the whole thing, right? Either like A dagger A, dagger, but since its Hermitian is the same, right? And so this cancel, and then you get back the A dagger A. So they are all consistent.
H is that.
No, not yet. So here I haven't proved it, right? Because I just assume that this is true, and then I say that if this is true, and then I can take P to be the square root of this positive operator, and it would work. So the usual way to show this is to first show this, right? So how do you do this, right? So you just write it out in full, and then you split this in, you take the square root, right? You split this into two parts. And this guy is just that guy. Sorry. Do I need, can we? Right, I need the square root. Right, that's good. Yeah, okay, sorry. Yeah, it's just that guy. And what would this mean? This means that for any vector psi under the action of A or under the action of its positive square root, the norm would still be the same, right? In particular, it would not map a non-zero vector to like a zero vector, for example. So we know that to say it another way, the dimension of the support and the dimension of the kernel of these two are the same. So the dimension can be the same, but it doesn't have to be the same subspace, right? The size and the same, so like the support of the two. So in particular now, it can. I just write something. But then what you can do now is that you can define a unitary that map these two spaces of the same size to each other, right? So in particular, it's this way. So if I define a unitary from the support of A dagger to support of A, and this can be written in equation like this, U. So here, right, so this is in this support, and then I map this to something in here. And you can define, of course, you can define this unitary in this subspace. You can define this map to be a unitary in this subspace because it preserves the length here. And then now you can just extend this unitary in this definition in the subspace to all space. And then you get the polar decomposition. For example, the A doesn't have to be invertible, right? So it can have kernel, but the unitary cannot have a kernel. Right? So basically, in the kernel of A, you can define the unitary to be anything. You just have to satisfy the constraint that this whole thing is this U is unitary. Yeah. Okay. Any questions about this?
In the complex solving,
yeah, that's a good point. Well, of course, there are other. Okay, it depends on the problem, right? It will show up, so you might remember that it will show up when. Okay, I don't know if you remember this, but for example, the Krauss operator can be any operator. It doesn't have to be a Hermitian or unitary. So Krauss operator express the effect of a measurement to the state, right? So for example, when we think about projective measurement, the Krauss operator is a projector, which is a positive operator. So in that case, we don't have U. But in general, in quantum information theory, you can have this. So this would be the effect of projection or like collapsing of the measurement, and then this would be some rotation add on. Yeah. Yeah.
So for polar decomposition, we look at the operator as just similar, right?
Yeah, in that context. Yeah. Just to add to the that explanation, you might remember that something like this from when you look at POVM element. So the P here would be the POVM element. So this is like the Krauss operator, the POVM element, and this is like an extra rotation that comes from that let you determine the post-measurement state. And so, for example, this is why from this polar decomposition, you can see why there can be, for a given POVM, the Krauss operator is not unique. In other words, there can be many Krauss operators that correspond to the same POVM, the same measurement, just because you can choose U to be anything. But of course, there's a meaning that's very particular to this. Yeah, it's not just some general like linear algebra problem. Right? It has a physical meaning in this case. But in the general sense, yeah, you are right that usually this is not there's something more useful than this. And the drawback of this in particular is that, well, at least from my experience, is that you form a group, so you can like apply. If you apply two unitaries, then it's still a unitary, right? But then this part is not a group. Yeah. So if you yeah, exactly. If you multiply like p how to say this okay, maybe I can talk to you afterward, but yes, yeah, it's like you can write Lie algebra of both of these elements, but the Lie algebra of P is not gonna be give a closed Lie subgroup. But and the way to fix it is to do the SVD. Right. No, the singular value, right? อันนั้นมัน machine learning นะ right. So for this is to say that any arbitrary linear operator or possibly not even, it doesn't even have to be operator, meaning it doesn't have to even map from the same to the same space. So it can be non-square matrix. This was SVD will still work. And it's sort of like diagonalization, but with two bases. So one from the U and from one the V dagger.
Even if you something like in that P should be identity auto.
Yeah. Right, because P would be the square root of U dagger U, but U dagger U is the identity. Yeah, I mean, you're right that the P has to be identity, right? Because P is this, right? And then if your A is already U, then this is just an identity, the identity, right? By definition. So here, how are we gonna prove this? Well, I don't know if I like sigma as diagonal or not. Maybe I want D. But never mind. Right. So this also takes advantage of the fact that both A dagger A and A dagger are positive, and in particular Hermitian, and so you can diagonalize both of them. So let's write, so I have to define, give some name to eigenvectors for A dagger A and A dagger. So let's say A dagger A has eigenvectors E with eigen values pj. So since this is Hermitian, then this can always be chosen to be orthonormal, right? And in the same way, so this has eigenvector f j, fk, whatever, and then eigenvalue q, so like qk. Right. Yeah, so we sort of have like this, like different, I don't know, eigen E1, E2, F1, F2. And in particular, there is a linear operator that's mapped back and forth between these two vectors. And well, what it is? Well, it's just A. So the claim is that A map from EJ to, well, I hope this is right, but if it's not, we can come back to fix it. So with some ordering of the eigenvectors, and how to see this? Well, so Fj, the way that we define it would be eigenvectors of A dagger, right? So let's say what happens if I let A dagger acting on A, acting on okay, this is a bit weird. Let's see. Okay. So right. So here, so I can think of this as A dagger A acting on EJ, right? Which is its own eigenvector. So it spit out the eigenvalue Pj, which is the same. So yeah, initially we have this and then we got the same thing back, but with some number in front. And so it means that A acting on EJ is proportional to the eigenvectors of A dagger. So in particular, you can get this proportionally constant just by normalizing this vector, right? This eigenvector. So we'll start by finding the norm, which is just this. Pj. And so that means that the eigenvectors, the normalized eigenvector of A dagger has to be this guy and then divided by the square root of P. Actually, yeah, we are about to finish. Can I erase this part of the book? Yeah. So in particular, it means that, well, since now we know that A maps from one basis of this to the other autonomous basis, right? So now we can write A in the direct notation, right? So it's mapped from EJ to Fj with this scaling constant. Oh, and by the way, we can always take the square root, right? Because we know that Pj is positive. Yeah, so both Pj and Qj are positive, right? Because these are positive operators. And so that's it for the SVD. Because now I can define these two unitaries to be the one that map from this basis to the standard basis. Right? Maybe let's do it. Yeah, let's. Or maybe did I say it in the wrong direction? I can define this to be okay. Now I already used EJ for this basis. So what do we want to call the standard basis? Yeah, and then this is just now I define another unitary here, right? So then I can write the whole thing as U V dagger and then diagonal matrix. Sorry.
This one.
Yeah. Right. Any questions or comment about this?
Why we have to take space in G?
Is to normalize it, right? Because here I'm calculating the square of the norm. Yeah, so I have to take the square root. Right. Yeah. Okay. So, yeah, so it's already 3 p.m. So, maybe, do we want to stop? Yeah, I think we should stop. Okay. That clock is dead. งั้นหยุดอัดขอบคุณครับเวฟ